All right, ready to dive deep. Today, it's Chapter 4 from your thermodynamics textbook.
Oh, yeah, chapter 4.
This is where it gets interesting, right?
Absolutely.
We're talking closed systems,
Yeah.
like a seal box, energy-wise.
Mm?
Our listener is a keen learner, by the way. We're assuming they're right there with us,
Yeah.
like already familiar with the basics.
I like it.
So Chapter 4, it gets into how energy works within these closed systems.
Yeah, it's like you've got this fixed amount of stuff, right? And we're going to see how energy plays around inside.
I'm thinking like pistons moving, engines, that kind of thing.
Exactly. Simple stuff that reveals a lot about how energy and work are all tied together.
Gotta love the first law of thermodynamics, right?
It's the foundation, isn't it?
Can't create energy, can't destroy it. It's got to move it around.
Transform it, yeah.
So in a closed system, how do we actually express that? Mathematically, I mean,
Well, you've got your classic equation, E in minus E out equals E system.
breakdown time. What's each of those bits actually mean?
Okay, so E in. That's all the energy coming into the system. Could be heat we're adding, work being done on it.
Like pumping up a tire,
Yeah.
that kind of work.
Yeah, exactly. Then you've got E out R. That's energy going OUT, heat escaping maybe, or the system doing work on something else -y.
I'm picturing that piston again, pushing outwards.
There you go. And then that last part, E system in.
Yeah.
That's how the system's total energy changes. Internal energy, kinetic, potential, all that jazz.
So if we add more heat than what leaks out, the system's internal energy goes up.
You got it. And usually that means its temperature rises too.
It's such a neat equation, though.
Yeah.
Simple but powerful.
It really captures the essence of energy conservation.
Chapter 4 gets into some fun scenarios, though, especially when we start talking about work. There's this thing, moving boundary work. Sounds kind of fancy.
It's actually very intuitive. Imagine, like you said before, a piston in a cylinder.
Oh, yeah, the classic setup.
If the gas inside expands, it pushes that piston, doing work on its surroundings. And the reverse, if we push the piston in, we're doing work on the gas.
So it's all about how much that boundary the piston moves.
Exactly. And we call this kind of work PdV work because it depends on the gas pressure, P, and the change in volume, dV.
There's a formula for that, right?
Yep, it's WB equals PdV.
Wait, hold on. Why is that a D and not a regular D?
Ah, keen eye. That little d there means the work done depends on how W the process happens, not just the start and end points.
What do you mean by how?
Well, let's say we're compressing that gas again. We could squeeze it down slowly, letting heat escape so the temperature stays the same, or we could slam that piston down fast.
Wouldn't that make it heat up?
Exactly. Both ways get us to the same smaller volume, but the work involved is different, and so is the final state of that gas.
So it's not just about where you end up, but how you get there.
Precisely. It's what makes thermodynamics so interesting, these path functions.
And I hear there's a visual way to see this. PV diagrams or something?
PV diagrams are fantastic. You plot pressure on one axis, volume on the other, and as your system changes, it traces out a path. The area under that curve, that's the work done.
So different paths meet different areas, even if they start and end at the same spots.
You got it. The path matters.
This is making so much sense now. So we've got the first law and how work sits into all this, especially with moving boundaries.
Yeah.
But then Chapter 4 throws another concept at us.
Yeah.
Specific heats. I feel like we all experience this without even realizing it.
Oh, for sure.
Like, you know how a metal spoon gets hot in your soup way faster than a wooden one?
Perfect example. It's all about how different materials store heat, their capacity for it.
So specific heat tells us how much energy it takes to heat up a substance by, say, 1 degree.
That's it. Specifically, it's the energy to heat up 1 unit mass of a substance by 1 degree Celsius or Kelvin.
But there are TW-specific heats, right?
Yeah.
CV and CP.
Right again. CV is when the volume's constant, so like that gas trapped in a rigid container. CP is for constant pressure, like when you're heating something in an open pot.
Wait, why does it need to be 2 different values? Shouldn't it just be 1 for a given material?
It's because heating something up while letting it expand is different from heating it up while keeping it squished.
Ah, so it's like if it can expand, some of that energy goes into pushing outwards instead of just raising the temperature.
Exactly. It's like the material's thermal personality changes depending on if it's free to move or not.
I like that. And some materials have wild personalities, right? Like
Yeah.
water.
Oh, water is a great example. Its specific heat is really high. That's why it takes forever to boil a pot of water.
Makes sense. And it's why oceans help regulate the planet's temperature.
Exactly. Water's a big player in climate because it takes so much energy to change its temperature.
So next time we're at the beach.
We can appreciate those ocean waves,
Yeah.
its amazing thermal properties.
Exactly. All right, so first law, moving boundaries, specific heats. It's amazing how much we can explain with these, right?
It is. And chapter 4 keeps going. It shows us how to actually calculate internal energy changes and brings in this thing called enthalpy.
Let's talk about internal energy first. We keep seeing this GASE. How do we figure out what that change actually is, especially with ideal gases?
With ideal gases, it's pretty straightforward. Their internal energy change is directly linked to their temperature change.
Okay, so hotter gas, higher internal energy. Makes sense.
Exactly. And we use those specific heat values we talked about earlier to calculate it.
So it all ties together.
Right. The formula is Leahy AVG, T2, T1. CVAVG is the average specific heat at constant volume over that temperature range, and T1 and T2 are the initial and final temperatures.
So if we know how much the temperature changes, and we know the specific heat, bam, we can calculate the internal energy change.
Precisely, and it emphasizes a key point. For ideal gases, internal energy only depends on temperature. It doesn't matter how we got to that temperature, just what it all lasts.
That simplifies things a lot.
It does. Now, enthalpy, chapter 4 introduces that as another important property.
Yeah, what enthalpy anyway? Why is it useful?
Enthalpy, denoted by H-ish, it basically combines internal energy with pressure and volume. The equation is H equal U plus PV.
HEQ plus PV. Okay, I'm writing it down.
It might seem a bit random at first, but it's super helpful, especially for processes at constant pressure.
Why constant pressure, though? What's so special about that?
Think about it. Lots of stuff happens at constant pressure, like heating a pot of water on the stove. The pressure inside stays pretty much the same, right? Atmospheric pressure.
Yeah, true.
So in these cases, enthalpy is great because it directly accounts for the heat going in or out of the system.
So instead of tracking internal energy, AD works separately. We can just look at enthalpy and get the full picture of energy flow.
Exactly. For constant pressure, the change in enthalpy IS, the heat exchanged with the surrounding.
That's pretty neat, like a shortcut for energy calculations.
It is. Okay, so we've got all these tools, these concepts. How does Chapter 4 help us use them to solve actual problems?
That's the key question, right? How do we put it all together?
Chapter 4 is big on a systematic approach, something you can apply to loads of different thermodynamic situations. First step, define your system. What exactly are we analyzing here?
Right, are we talking about a fixed amount of gas or a flowing stream or what? Got to be clear about that.
Absolutely. Then you apply that trusty first law, the energy balance equation. E in, E out equals E system.
And this is where it gets tricky, right? Figuring out all the energy flows involved. Heat, work, changes in internal energy, maybe kinetic energy, potential energy.
It's like detective work, energy style. And here's where all our concepts come in handy. Moving boundary work. Use PDV. Constant pressure. Enthalpy's your friend. Specific heats tell us about internal energy changes.
Like having a toolbox full of specialized gadgets.
Exactly. Once you've accounted for all that energy flowing around, you can rearrange the equation to solve for whatever you're looking for. Final temperature, heat transferred, work done, it's all there.
The energy balance equation is like the framework, and then we fill in the blanks with our knowledge of specific heats, enthalpy, all that good stuff.
That's a great way to put it. Chapter 4 even gives us loads of examples, like that one with the rigid tank full of air.
Oh yeah, I remember that one.
Classic closed system problem. Fixed volume, so no moving boundary work to worry about. If we assume it's well insulated, we can ignore any heat loss too. Simplifies things a lot.
So the only energy flow, the heat we add, and that goes straight into increasing the air's internal energy.
Yep. And since internal energy for ideal gases is tied to temperature, we can then calculate how much the temperature goes up based on the heat and the air's specific heat.
Elegant and powerful.
It is. And it's not just for textbook problems. This is the foundation for analyzing real systems. Engines, power plants, refrigerators, even the Earth's climate.
That's what's so cool about thermodynamics. It's a window into how the universe works, from tiny atoms to giant stars. It's pretty mind-blowing how it all connects.
It is.
So big picture as we wrap up Chapter 4 here, what's the most important thing for our listener to take away?
Ooh, good question. I'd say it's the sheer power of that first law applied to these closed systems.
Right. It's like the guiding principle, the rule book for how energy behaves.
Yeah. And we've got these tools now, right? Moving boundary work, specific heats, enthalpy.
We can solve some pretty complex stuff with these.
Exactly. Chapter 4 gives us the tools, A and D, the mindset. Define the system, apply that energy balance equation, figure out all the energy flows.
It's like learning a whole new language, the language of energy.
Love it. And as we get fluent, we start seeing the world differently. Everything's an energy exchange.
Chapter 4 is just the start,
Oh,
though.
totally. There's so much more to come. Thermodynamic cycles, engines, power plants. It just gets more and more exciting.
Whole new worlds to explore.
It is. It's been awesome diving into this with you and with our listener out there.
And for our listener, keep those brains buzzing. This is just the beginning of your thermodynamic journey.
Keep exploring, keep asking questions. There's always more to discover.
Exactly. That's what makes it fun.